Welcome on board the Webb telescope. Take off in 5, 4, 3, 2, 1 as we twist past support points. Furthermore, worlds watch out for exoplanets and detonating stars. Webb's mirrors are unfurling to uncover the most dynamic perspectives on the universe. Our objective, the amazing heavenly nursery inside Orion's sword. Tie in tight as we plunge inside the cloud, where our instruments will analyze light from the early universe and top into mists shaping new worlds. Heavenly revelations await. Our experience begins. Picture number 1. A more intensive gander at the Orion Cloud. The Orion Cloud is one of the most notable objects in the night sky, situated around 1,350 light-years from Earth, just beneath the 3 bright stars that make up Orion's belt. It has long interested cosmologists and stargazers alike. At its center lies the Trapezium Cluster, a gathering of youthful, enormous stars that discharge extraordinary ultraviolet light. This radiation illuminates the surrounding billows of gas and dust, making the cloud's recognizable gleaming appearance. Embedded within these mists are many fascinating galactic objects and peculiarities that are still being studied today. Young stars, otherwise known as protostars, are still forming out of the thick molecular mists behind the Trapezium Cluster. As the protostars develop, they push out lively planes and whirling disks of dust and gas known as protoplanetary disks. These disks are where planets may ultimately form. Scientists have also found brown dwarfs in the cloud, strange astronomical objects too small to become stars, but too large to be planets. Even free-floating planets, not orbiting any star, have been identified. Another area of focus are photodissociation regions. These are where the harsh ultraviolet light from the stars interacts with the molecular mists, causing chemical reactions that change the composition of the gases. Studying these transition zones helps us understand how massive stars impact the environment around them. Cosmologists use the cloud as a natural lab to observe different phases of star formation and early planetary system development. The new images were taken using the near-infrared camera CAM on board the James Webb Space Telescope. NIRCam can detect infrared light, allowing it to see through clouds of gas and dust that block visible light. It made 2 large mosaics, one stitching together multiple individual observations. One mosaic used the camera's shorter infrared wavelength filter for the highest possible resolution, revealing complex details in the protoplanetary disks and outflowing jets swirling around young stars. The longer wavelength mosaic revealed a complex web of different types of dust grains and polycyclic aromatic hydrocarbons, PAHs, which are carbon-containing molecules spread throughout the cloud. By studying the Orion Cloud with exceptional clarity and scale, astronomers hope to uncover more secrets about how stars, planets, and planetary systems are born in these heavenly nurseries. What additional peculiarities or astronomical objects could future observations uncover in this famous area of star formation? Only further study with powerful new tools like the James Webb Space Telescope will tell. Picture number 2. Investigating a galaxy up close. The new images from the James Webb Space Telescope offer a rare glimpse at a fascinating galaxy called NGC 6822, located about 1.6 million light-years from our own Milky Way. Despite appearing as only a faint smudge in small telescopes due to its significant distance, Webb's observations strip away clouding gases and stardust to reveal a galaxy rich in heavenly treasures. Within NGC 6822's irregular shape is a bright spherical mass. After closer examination, astronomers determined this is actually a globular cluster, a round gathering of thousands of old stars tightly orbiting the galaxy. Globular clusters are found surrounding larger galaxies like our own and contain some of the very first stars formed in the early universe. Its clear view here suggests Webb will uncover more of these celestial relics hiding in other distant galaxies. While invisible to our eyes, Webb sees infrared light wavelengths just beyond the red end of the visible spectrum. To translate these into colors we can understand, the telescope assigns blue to the hottest, youngest stars emitting short infrared waves, and warmer hues like orange and red to cooler, aging stars emitting longer infrared waves. This process maps wavelengths to colors, allowing us to see the rich heavenly populations within NGC 6822 in a format our visual cortex can interpret. With its sharper view into distant galaxies like this one, Webb will uncover more about how irregular galaxies like NGC 6822 formed throughout cosmic history. Are there additional hidden globular clusters waiting to be discovered further back in time? New observations from this powerful observatory might help reveal when the first stars and galaxies illuminated the young universe billions of years ago. Picture number 3. A closer look at the magnificent swirling arms of galaxy M51. Found about 31 million light-years from Earth, the stunning spiral galaxy known as M51, or NGC 5194, is shown here in a fresh new light thanks to observations from the James Webb Space Telescope's mid-infrared instrument, MIRI. MIRI's infrared imaging capabilities allow us to peer through the dust and gas that make up M51. The dramatic arms reveal intricate, fiber-like structures woven throughout these wispy rings, forming a web-like design across the galaxy's disk. The visible swirling arms seen emanating from M51's center are believed to have been influenced by the gravitational pull of M51's much smaller cosmic neighbor, the dwarf galaxy NGC 5195. As this smaller galaxy passed nearby in the past, its gravitational forces may have helped pull and compress the gas and dust within M51's outer edges, complementing the formation of its striking spiral structure. How exactly did these two galaxies interact? Cosmologists estimate NGC 5195 passed extremely close to M51, based on computer simulations of the encounter, while MIRI highlights the dusty filaments inside. The M51 Webb's close-to-infrared camera, ANARCM, is well suited to capture the gleam of hot, youthful star groups that have recently formed. ANARCM focuses on the ionized gas surrounding these dense, young star networks, illuminating pockets of bright plasma dispersed among wispy dust paths. By observing M51 across both near and mid-infrared wavelengths, we gain a more complete image of the complex interplay between infant stars and the dense clouds of particulate matter that ultimately birthed them. At a distance of more than 31 million light-years, we see M51 as it appeared in the past. Its perfect spiral structure gives astronomers a glimpse into the processes that shaped galaxy formation in the distant past. Webb promises to reveal many more cosmic wonders like M51 that were previously invisible to us. Continued observations with this powerful new observatory will undoubtedly yield new insights into the dance of matter, stars, and gravity across the universe. Picture number 4. Looking deep into the star-forming galaxy NGC 568, let us explore the vast barred spiral galaxy NGC 568, located around 170 million light-years from our Milky Way in the constellation Virgo. Through the powerful infrared cameras of the James Webb Space Telescope, we can see this galaxy in remarkable clarity, revealing many fascinating phenomena occurring within. At first glance, across Webb's image, intricate ringlets of dark cosmic dust intertwined with clusters of bright blue stars swirl across the center of NGC 568. Upon closer inspection, a distinct bar-like structure extending horizontally through the galactic center comes into focus. Made of dense molecular gas and dust, this bar serves as a nursery, fueling the birth of new stars. Emerging from the bar are several nebulae glowing in infrared light, massive clouds of ionized hydrogen gas heated to tens of thousands of degrees by intense radiation from young stars forming within. The nebulae display a variety of shapes. Some appear fluffy and amorphous, while others have sharply defined edges. Their diverse appearances provide clues about differences in gas density, temperature, pressure, and composition across each star-forming region. Astronomers also observe ominous shadows of thick molecular gas and dust scattered throughout, some containing dense cores where even more stars may be gestating over time. Strong stellar winds and radiation will shape and disperse these stellar nurseries. ALMA submillimeter observations have previously revealed more than 12,000 cold, dense molecular clouds and clusters within NGC 568, alongside Hubble Space Telescope imaging that recorded more than 10,000 star clusters. Combining these datasets with Webb's new high-resolution infrared mosaics gives astronomers an unprecedented multi-wavelength view into the complex interplay between gas, dust, stars, and stellar evolution across this galaxy. They can study the physical processes shaping each stellar nursery on scales from single clusters to the galactic-wide level. Transient phenomena, like asteroids, also make appearances. While focused on NGC 568, 3 small streaks of light, corresponding to asteroids passing through Webb's field of view during multiple exposures, are visible. These subtle signs of our own solar system's location create color trails against the more constant extragalactic background, which would have escaped previous telescopes. With its clear panoramic views cutting through the darkening dust lanes, the James Webb Space Telescope is uncovering the wondrous processes driving star formation behind the stellar bars across our universe's grand spirals. Future observations of NGC 568 and other galaxies promise to further illuminate these enduring cosmic mysteries. Picture number 5. Taking a closer look at star cluster NGC 346, let us examine star cluster NGC 346. Located around 160,000 light-years away in our neighboring galaxy, the Small Magellanic Cloud. To view this remarkable stellar nursery, astronomers have combined observations from some of Earth and space's most advanced observatories, including the James Webb Space Telescope, Chandra X-ray Observatory, Hubble Space Telescope, and others. By merging data across the electromagnetic spectrum, from high-energy X-rays to infrared invisible light, researchers have created stunning composite images revealing intricate phenomena within NGC 346 that individual instruments cannot detect alone. For instance, Chandra's X-ray vision maps areas of blazing temperatures, where rapid star formation is unleashing powerful stellar winds. Webb's infrared eyes peer through darkening cosmic dust clouds to highlight nascent stars still forming within dense cores. New details are coming into focus about star birth within NGC 346. Chandra data pinpoints more than 100 distant stars with intense stellar coronas, while Webb reveals over 24 protostars still shrouded in dusty cocoons. By cross-referencing observations taken years apart, astronomers are tracking stellar developmental cycles and dynamic outflows shaping the surrounding nursery over centuries. Several questions remain. How do the earliest stages of star formation proceed on small scales? Are there patterns in how newborn stars cluster together or disperse into the galaxy? With preceding facilitated perceptions utilizing various frequencies, specialists desire to collect time series scenes clarifying the complex processes fueling heavenly advancement, from birth to development, inside NGC 346 and beyond. Multimer stargazing is providing a more complete picture than ever of how stars, the building blocks of all cosmic structures, initially arise across our vast universe. A deeper examination of the combined data has revealed captivating elements within NGC 346. Chandra's X-rays reveal over 100 massive young stars encased in glowing hot plasma, their powerful stellar winds carving twisting cavities within the dense star-forming cloud. Meanwhile, Webb's infrared view penetrates the dust, spotting more than 24 stellar objects just beginning to show signs of life at the cloud's core. Surrounding these nascent stars, Webb images reveal gas filaments resembling swirling eddies or atmospheric flows. Astronomers believe the surrounding cloud material holds marks of the intense rotational movements from its initial gravitational collapse. Over significant periods, feedback from brilliant stars will either disperse or further shape these swirling structures, influencing future generations of star birth within NGC 346. Comparing observations taken years apart shows the changes that occur swiftly on human timescales but slowly from the perspective of young stars. Some objects visible as direct sources to Chandra are now faint and obscured by new bursts of dust illuminated by Webb. Meanwhile, other areas have cleared entirely as stellar winds blow cloud material outward, gradually unveiling new stellar inhabitants. By piecing together data across the electromagnetic spectrum and over many years, astronomers are creating time-lapsed views of NGC 340 SIXS dynamic development. Further observations may reveal whether clusters like this follow predictable star-forming cycles or if stochastic events, like supernovae, also shape their development in this dynamic stellar nursery. Image number 6. Unraveling the mysteries of Messier 74. Astronomers have focused on the grand spiral galaxy Messier 74, located around 32 million light-years from Earth. By combining observations from the Chandra X-ray Observatory, the James Webb Space Telescope, and other instruments, researchers have constructed vast composite images revealing new layers of activity within this distant island universe. Messier 74 resides in the constellation Pisces, its luminous spiral arms stretching over 100,000 light-years. Chandra's high-energy X-ray vision maps extremely hot gas, identifying over 150 towering regions erupting with brilliant stellar explosions in supernovae. Meanwhile, Webb peers through the galaxy's swirling dust lanes, illuminating bustling star-forming nurseries where giants of the future are just taking shape. What further insights could these combined images reveal about M74's evolution? Chandra pinpoints areas where aging stars are seeding the universe with elements through spectacular final fireworks. Webb images reveal patches of dense gas contracting under their own gravity, likely to soon give birth to clusters of new stars. The voracious black hole at the galaxy's center also emerges, its influence detected by unusual X-ray flares. Observing M74 across the full breadth of the electromagnetic spectrum, astronomers gain a layered perspective that no single telescope could provide. New questions come into clearer focus. How do obscure dust lanes influence star formation across the spiral arms? What triggers periodic outbursts from the central black hole? With coordinated investigations, the full story of how galaxies dynamically evolve may gradually come to light. Further exploration of M74's composite images has revealed intriguing activity throughout its spiral arms. Chandra's X-rays expose over 150 mushroom-like supernova remnants billowing outward from stellar explosions, enriching the universe with elements like silicon, carbon, and iron recycled from older star generations. Webb's infrared view spots areas peppered with vibrant young clusters, scattered across M74's core, still nestled within dense stellar nurseries. Comparisons with past Hubble images reveal these clusters steadily dispersing across the galaxy's center over decades. Energetic outflows from massive stars are thought to shape gaseous ringlets, slowly dispersing the clouds that give birth to them within M74. The galaxy's characteristic barred structure shows long filaments of dust straddling its core in Webb's view. Astronomers believe gravitational interactions between gas, stars, and a supermassive black hole account for the twisting bar of M74 over millions of years. Winding density waves propagating from the bar may also have triggered new episodes of star formation along the outer arms. By piecing together clues seen across the light spectrum, cosmologists are building a dynamic timeline of M74's evolution over cosmic history. Further multi-wavelength observations in the years to come may reveal how external interactions with neighboring galaxies and the intracluster environment also drive dramatic changes within this iconic island universe's spiral landscape. Image number 7. Unraveling cosmic evolution across cosmic time. The James Webb Space Telescope has trained its mirrors on the famous Hubble Ultra-Deep Field, capturing galaxies over 13.4 billion light-years away in a fraction of Hubble's observation time. This tiny patch of sky contains an estimated 10,000 galaxies, offering an unparalleled window back in time. Located in the constellation Fornax, the Hubble Ultra-Deep Field covers an area smaller than a grain of sand held at arm's length, yet within this fragment of the universe, Webb has observed some of the most distant galaxies to date, over 13 billion light-years from Earth, seeing back to within just 500 million years after the Big Bang. What insights might Webb's data provide about early galaxy formation? Its infrared instruments can penetrate obscuring dust clouds within young, primitive galaxies, revealing regions where the first massive stars are stirring. By identifying protogalaxies in various evolutionary stages across such vast timescales, astronomers aim to reconstruct how properties like morphology, size, and star content have changed since the early universe. When combined with over 20 years of optical, infrared, and X-ray data on these galaxies from both space and ground-based instruments, Webb's high-resolution views are merging into a more robust picture. Questions surrounding the onset of star formation, heavy element production through stellar deaths, and the processes sculpting galaxy mergers across cosmic timelines can now be addressed as never before. With continued coordinated observations, cosmologists may one day answer profound mysteries regarding how the various magnificent systems populating the present universe initially rose up out of the haziness of the early universe web. Observations have uncovered subtle details within Hubble's ultra-deep field galaxies that were previously concealed. Young star clusters are visible, embedded within dusty stellar nurseries, their short, energetic lives already sculpting the surrounding gas through stellar winds and radiation pressure. Protogalactic structures are also emerging. Massive clusters of dense, star-forming molecular gas continuously merging under gravity. Over generations, astronomers speculate that within these overdense areas, runaway collisions will give birth to some of the earliest truly massive black holes, which then seed the growth of the largest structures detectable today. By comparing positions and morphologies of galaxies across observations spanning decades, subtle changes become clear. Some objects have evolved into elliptical shapes, while others appear amidst dramatic mergers, unleashing bursts of new star birth visible to Webb through its infrared capabilities. Careful examination of spectra extracted by Webb has also revealed signatures of heavy elements. Even in the most distant galaxies, evidence of past generations of stars evolving and dying. Further spectroscopic studies may reveal when the first heavy element production became widespread throughout the universe. Through its sweeping views of the Hubble Ultra-Deep Field, the James Webb Space Telescope is helping astronomers build the first coherent picture of galaxy formation, from their earliest embryonic origins to the splendid spiral structures that pervade today's cosmic landscape. Image number 8. Webb unveils mysteries of the icy giant Uranus. The James Webb Space Telescope has captured its first image of the distant planet Uranus, located approximately 2.9 billion kilometers, or 19 light-hours, from Earth in the outer reaches of our solar system. At this distance, Webb was able to observe fine details with exceptional clarity, like thin, wispy clouds swirling within Uranus' azure atmosphere and the arrangement of dark and bright rings encircling its equator. Uranus bears a unique axial tilt of nearly 90 degrees compared to other planets, leading its poles to experience extreme seasons, with one pole facing the Sun for over 20 Earth years before turning to darkness for the same duration. When the Voyager 2 probe flew by Uranus in 1986, its southern pole was in summer. However, more than 30 years later, Webb's image shows the South Pole oriented away in winter darkness. Despite this, astronomers were surprised to detect a subtle bright spot at the center of the south polar cap, visible even in darkness. What properties allow this feature to glow while the surrounding cap remains dim? Future observations may help determine the polar cap's formation and seasonal cloud behavior. Webb also resolved 11 of Uranus' 13 known rings in just 12 minutes of observation, revealing new insights into this enigmatic planet's diverse ring architecture. With its powerful instruments, the James Webb Space Telescope is poised to unravel lingering mysteries about Uranus and assist scientists in better understanding planetary formation and evolution across our vast cosmic neighborhood. Webb's detailed images provide rare views of atmospheric banding and cloud features swirling atop Uranus' predominantly icy mantle. Delicate wisps and patches in pale blues and aquas decorate the gaseous giant, driven by winds often exceeding 300 miles per hour. Infrared observations also shed light on Uranus' internal heat source, which drives convective currents within the hydrogen-helium atmosphere above an interior likely dominated by dense ices of water, ammonia, and methane. Variations in observed cloud structures at different wavelengths may correlate with depth and atmospheric temperature profiles, yet to be fully demonstrated. Particularly noteworthy are the dynamics influencing Uranus' mysterious ring system. Webb clearly identifies narrow bright curls and diffuse dark rings, some only hundreds of kilometers wide. Their skewed and warped shapes suggest a complex orbital evolution influenced by gravitational interactions with Uranus' 27 known moons. By monitoring atmospheric properties and ring changes over seasonal, short-term, and long-term timescales, scientists may gain new insights into weather, internal structure, and the primordial ring particle composition of this distant giant. Coordinated multi-wavelength observations using Webb and other observatories promise new discoveries about Uranus, broadening humanity's understanding of planetary science. Image number 9. Exploring the mysteries of Crux, the Southern Cross. Set against a backdrop of the Milky Way, the small but distinctive constellation Crux shines brightly in the night skies visible from the southern hemisphere. Also known as the Southern Cross, this asterism has long held cultural significance for those residing in regions below the equator. Crux resides within our galaxy's disk. Situated roughly 800 light-years from Earth, it contains 4 noticeable blue-white stars that together form a cross shape under 5 degrees in width. The brightest of these, Alpha Crucis or Acrux, is actually a binary star system whose 2 parts are separable even with modest amateur telescopes. Nearby, Beta and Gamma Crucis are also multiple star systems, as is Delta Crucis, found at the bottom of this famous asterism. What more can we learn about this captivating assembly of heavenly gems? Careful investigation of the Crux stars' spectral patterns might reveal clues to their internal structures, ages, and development. Observing their movements against more distant backgrounds similarly provides insight into the collective mass and structure of our Milky Way. Do interactions between these close-orbiting members of multiple star systems influence outcomes like supernovae, which seed heavier elements throughout cosmic nurseries? Continued observations over long timescales might reveal changes unfolding among Crux's brilliant residents, enhancing scientific understanding of stellar populations within our universe's remote arms. Perhaps future instruments will detect previously unknown complexities lurking within this small yet renowned southern constellation, forever etched into the myths and cultures of peoples under the southern skies. In the sprawling constellation of Ophiuchus, the Rho Ophiuchi cloud shines brightly 400 light-years from Earth, visible only through infrared telescopes. This vast cloud of gas and dust harbors a bustling nursery where new stars are forming right before our eyes. Spanning over 50 light-years, the Rho Ophiuchi cloud contains more than 200 dense molecular clouds that appear outlined against its vibrant diffuse glow. Infrared observations reveal these molecular clouds are dense with elements like hydrogen, which concentrate under gravity's pull. Within certain clouds, protostars have already emerged, growing more massive by accreting material from disks surrounding their cores. It remains a mystery what triggers certain clouds to birth stars while others remain dormant. Does a nearby supernova initiate the process, or do pressure waves rippling through the cloud launch gravitational collapse? Observing this region over centuries might uncover which environmental factors influence stellar evolution at its earliest stages. Astronomers speculate that a new generation of stars will eventually emerge from Rho Ophiuchi, scattered throughout the Ophiuchus constellation. Perhaps some will resemble our own nurturing Sunday. By deciphering the nurturing mechanisms within this stellar nursery, scientists hope to gain insight into how starbirth has shaped our Milky Way across cosmic history. New stars illuminate both night skies and humanity's understanding of the universe. Within the cloud's dense pockets, infrared telescopes detect infant protostars cloaked in thick layers of dust and gas. Some objects, like the Rho Ophiuchi protostar, have grown large enough to host disks of swirling material in hydrostatic equilibrium, where emerging planets may already be forming. Amidst the clouds are dynamic emission-lit globules, strikingly shaped by radiation and winds from the nearby O-type star Antares. Multi-wavelength analysis of these structures examines how energetic feedback interacts with dense cloud structures. Some globules shield small protostellar embryos, while others are dispersing under intense stellar winds. The young stars within the cloud showcase a range of characteristics. Some T-Tauri variables exhibit powerful stellar flares, while brown dwarfs, too small for full hydrogen fusion, have also emerged from the clouds. Studying this diverse array of young stars in varied developmental stages provides clues to mass-dependent formation pathways. With its penetrating infrared vision, the James Webb Space Telescope will continue unraveling secrets within this busy stellar nursery. Comparisons with past observations may also reveal how environmental factors, like cloud collisions, influence the episodic pace of star formation across Rho Ophiuchi's turbulent stellar nursery. Webb reveals a cradle of stars in Orion, over 1,350 light-years away within the sword of the mighty hunter. Orion glows as one of the sky's brightest star nurseries, the Orion Nebula, illuminated by the hot young stars of the trapezium cluster. Wispy ribbons of dust and luminous hydrocarbon clouds have been sculpted into haunting silhouettes against the nebula's lush glow. Webb's new long-wavelength mosaic, stitched from numerous NRCam images, offers an unparalleled view of this stellar cradle. Delicate strands of dust winding through the nebula are outlined by organic compounds tracing photodissociation regions along the borders between starlight and darkness. Embedded within clouds of dense molecular hydrogen, protostars linger in various stages of development, some shrouded in thick cocoons, while others boast swirling disks, distant worlds in the making. What more mysteries exist within the nebula's nooks and crannies? Does energetic radiation from the trapezium's O and B-type giants influence nearby starbirth? Are the possible planetary systems detected around young stellar objects viable environments, or were planets stripped away by intense outflows? Future observations using Webb's suite of instruments may help piece together a more detailed timeline of stellar evolution in this iconic stellar nursery. With each new revelation, cosmology inches closer to answering age-old questions about the processes that have shaped our very existence among the stars. Within the Orion Nebula, Webb's high resolution reveals intricate structural details down to scales of just a few astronomical units. Delicate jets of ionized gas are seen shooting from young stellar objects as they interact with disks and surrounding material. The brightness and morphology of these jets may indicate varying accretion rates onto the protostars over time. Studying these elements provides insights into the cyclical nature of star and planet formation. Embedded within the cloud are lower-mass brown dwarfs, still warm from the heat of their formation yet lacking nuclear fusion. Their distribution and properties offer insights into the substellar mass spectrum emerging from the stellar nursery. By capturing spectra across the nebula, Webb can examine how radiation and shocks produced by the trapezium stars ionize the gas clouds, affecting chemistry, temperatures, and pressures. This radiative feedback may help regulate the efficiency of star formation across Orion's dense cloud regions. Repeated observations could reveal subtle motions of nebular features or variable stars, unveiling 3D motions and structures within the vast complex. Coupled with historical data, this traces conditions in the nebula from hundreds of thousands of years ago when the trapezium stars were very young. Their evolving interplay shapes new generations of stars born here today. I hope you enjoyed this look at the Orion Nebula and Webb's discoveries. Like and subscribe so you don't miss upcoming videos as we explore more cosmic objects with Webb. Each new image brings us closer to understanding our place among the stars. My question: what would you like Webb to see next? Let me know in the comments which nebula, galaxy, or exoplanet interests you most. Thank you for joining me on this journey.